Hello, today we're going to go over the Honors Chemistry Chapter 8.1 notes on balancing chemical equations. So yesterday we talked about a chemical reaction being the rearrangement of atoms to form new molecules. We have three examples of chemical reactions here below. We have hydrogen gas, that's H2, plus oxygen gas, O2, forming water in the liquid phase. That's what this L stands for. And we also have sodium, which would be a solid metal, plus chlorine gas, making sodium chloride, which is table salt. So the reactants on the left of the arrow end up looking and acting nothing like the products on the right side of the arrow. Hydrogen peroxide, that's maybe in your medicine cabinet in the brown bottle, will decompose, that means break down, into oxygen gas and water in the bottle over a very long period of time. It's a very slow reaction. How do you know a reaction has taken place? Tell me a few ways that you know a reaction has taken place. So yesterday we talked about a few things, one of them being bubbles. So if you see bubbles being given off, if you see light coming out, or if it's giving off heat, these are some indications that you have a reaction. So for combustion, for example, anything burning or exploding would give off a lot of light and heat. And another one would be a color change. So if you have a change in color, you know a reaction has maybes. There's some physical processes that change the color of a sample, but usually if a color changes, it's going to be a chemical reaction. So that's how we know a reaction has taken place. I want you guys to remember that the reactants are the ones on the left side of the arrow up here, and the products are the ones on the right side. So reactants go in and products come out of a chemical equation. The equation is a way to represent the reaction with symbols and formulas. So we have three chemical equations written right here. So this is how we write an equation in chemistry. We use the plus sign, just like in math, to mean we're adding these two together. But instead of an equal sign, we have an arrow because you have two things that are turning into something new on the right. Circle the reactants in the equations above and put a box around the products. Take a minute to do that in your notes. All right, so my reactants, let's do it in red. These are my reactants. Everything on the left of the arrow are the reactants, and put a box around the products. Let's make that box turquoise. So these are my products right here. Okay, sometimes we have one product, sometimes we have two, or you could have many different products, like 3 or 6 or however many there are. The coefficient is going to be the number that we write in front of the molecule. So for example, up here we have a big 2 in front of the H2O. So the formula H2O tells us what the molecule looks like. It means you have 1 oxygen and 2 hydrogens. So that's this little Mickey Mouse molecule right here. The big 2 in front is called a coefficient. It tells you how many of those molecules there are. But in our class, it usually means moles. So I might have 2 moles of water. Okay, and 1 mole of water is 18 grams. So 2 moles would be about 36 grams of water. Okay, which is a reasonable amount. That's like a very small half of a cup of water would be about 36 grams. I want you to draw 3 carbon dioxide molecules in your notes. Here's one, so I'm going to go ahead and draw the other 2. There's my carbon and another carbon and 2 oxygens on either side. Okay, oxygen and carbon are roughly the same size. So they look something like this. And what I really want you to notice is that these are different than a salt. A salt is a crystal lattice, and these little molecules are individual little units. So they're floating around. Since this is carbon dioxide, it's going to be a gas at room temperature. So these are moving around quickly in all directions, and they might bump into each other and bounce off of each other. They're not going to be stuck together unless we cool them way down and then we had dry ice, in which case they would be all stacked up, but they separate very easily into their individual molecules again. And then that's sublimation, which is for another chapter. All right, we looked at a precipitate yesterday. Remember, a precipitate is a solid that forms from aqueous solutions. That just means water solutions. So you have 2 test tubes or beakers or whatever you're using filled with some kind of usually clear. Sometimes it can be like a light blue or a little bit cloudy. So we have water in these guys, and there's some kind of dissolved ions that we can't see because they're dissolved, so they're tiny. Okay, we'll drop turquoise and green. Those kind of look the same, but they're different. When we mix the two together, these little ions stick together and they make a solid, and that was when we put these together, we saw the video yesterday. We mixed them up, and what we got was a bright yellow precipitate when they stuck together, and then they're going to sink down to the bottom. Eventually, it'll all sit at the bottom. So that's a precipitate. You do need to know the diatomic elements. So those are the elements that are always in twos. Okay, they always are found in pairs because they're more stable. So the molecules that are found as diatomic, the elements that are found as diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. One way to remember those 7 is the rule of 7. So it says that you start with element number 7 on the periodic table. Let's look at that periodic table. So right here, element number 7, nitrogen, and you're gonna, there's 7 of them, and they make the shape of a 7 very roughly. It's more like an upside down L, but you have nitrogen, and then oxygen right here, then fluorine, then you go down chlorine, bromine, iodine. So those 6, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, plus hydrogen, which is way over here by itself because it has 1 valence electron. It's in group 1, but it's not really an alkali metal like the other ones. So hydrogen is always found in pairs. Okay, hydrogen, and then nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. These are the 7 diatomic elements that you need to remember. All right, some symbols that we use in our chemical equations. The arrow, okay, so just a single simple arrow. It's down a little bit low, but it just looks like this. It's used to show yields or produces, or sometimes we say makes. So up above we said hydrogen plus oxygen makes water. This is a double arrow. It's a little bit shifted down below where it's supposed to be, and sometimes you'll see it written like this with little half arrows because they go together better. This is for a reversible reaction. So that means that, for example, water, you can take hydrogen and oxygen and make water. That would be the right facing arrow. Or you could take the water and run electricity through it, and it will bubble and give off hydrogen and oxygen, which is the opposite reaction. It's the one going left. So that is a reversible reaction. That's going to be important later. The S in parentheses stands for solid. We can also write this downward facing arrow because, like we talked about, a precipitate is going to settle down to the bottom of the beaker, whatever you're putting it in. So a precipitate can be a downward facing arrow in the equation. Liquid, that one's a little hard to see. It's a cursive L. It looks like this. Okay, and we use a cursive L because just a regular L in Arial or Times looks like a 1. Aqueous means it's dissolved in water. So if you take sodium chloride, salt, and dissolve it in water, you will have an NaCl AQ, or aqueous solution. So that's what AQ means. It means it's dissolved in water. G is for gas, as is the up arrow, because bubbles will go up if they're formed. So if a gas is formed, it's going to go up. You can use the G or the up arrow. Usually it's a G. This triangle over the arrow should look like that. And that is, the triangle stands for heat. Okay, so heat is added to this reaction in order to get it to go. And this one you might have seen when you were talking about photosynthesis in biology. this is the symbol for light being needed. So if you remember, the Greek letter nu right here is for frequency. So you have H, which is Planck's constant, you don't need to know that, times frequency. That tells you the energy of light that is needed for that reaction to happen. So plants need light to do photosynthesis, and you would have an arrow that looks like that. All right, we kind of already discussed this. How do we know reaction's occurring? If it gives off energy, is heat or light. If it bubbles and gives off a gas. If you form a precipitate, you know a reaction has taken place. And if there's a change in color, it's usually a reaction, a chemical reaction has occurred. This is not your homework. These are optional. If you want more practice, you can look there. What we need to finish up is balancing equations. So the law of conservation of mass says atoms cannot be created or destroyed in a chemical reaction. Nuclear reactions are an exception that we won't get into. They do have a very small change in mass because mass is converted to energy, because mass and energy are kind of interchangeable right here. But that's only in a nuclear reaction. So we're talking a power plant or in the sun and not in our lab classroom. Okay, so what does law of conservation of mass have to do with balancing equations? Basically, whatever atoms you start with at the beginning of a reaction, so on the left of the arrow, you have to have at the end of the reaction on the right side of the arrow. So down here, we looked at hydrogen peroxide turning into oxygen and water. And there's a lot of ways to balance these. One way is to draw these molecules. Another way is to make a little T-chart down below on each side of the equation and put what elements you have here and then balance them that way. So one hugely important rule is that you are only allowed to change the coefficients. You don't ever change the subscript, because that's like making your own reaction when what you're really doing is balancing the reaction that is given to you. So this is the reaction that is being observed. You don't want to put, for example, if I put a little 2 down here, that's saying hydrogen peroxide turns into hydrogen peroxide. That's not the equation that they were asking for. So don't change subscripts ever, ever, ever. What we want to do is put numbers in front, put a coefficient out in front that's going to help balance the number of atoms. So as it is, I have oxygen on the left and hydrogen. Keep them in the same order, oxygen and hydrogen, and then count how many you have on each side of the arrow. Okay, so the arrow is kind of like, it's a division between them, and we want the left of the arrow and the right of the arrow to be equal. I have 2 oxygens and 2 hydrogens on the left. On the right, I have 2 hydrogens, but my oxygens are unbalanced. And here's what I do. You don't have to do it this way, but this is the way I prefer. I have 2 plus 1. Now I could have written 3, but when I change a coefficient here or here, I'm only going to change one of these numbers. So that's why I like to keep them separated and then write the total. Okay, so these are not balanced. I have 1 more oxygen on the right than I had on the left. So I need more oxygens on the left. And again, the only thing I can do, I'm going to do it in red, is put a big coefficient out in front. If I double this whole molecule, that means this becomes multiplied by 2 and this becomes multiplied by 2. And I have 4 of each now. That's going to allow me to fix this side. Okay, so if I put a 2 in front of the O2, that's not going to help my hydrogen be balanced again. So I'm going to try a 2 right here. And what that did is that doubles the hydrogen. So now my hydrogens are balanced, and that changed this 1 into a 2. So I had 2 plus 2 now, which is 4. Okay, so now they're all balanced. So this right here is my balanced equation. Okay, that's my balanced equation. I want you to try the next few, and I'll go over them with you in a second. So go ahead and try those now. All right, so did you make your T-chart on each side? And you have oxygen and hydrogen, oxygen and hydrogen. We had 1 oxygen and 2 hydrogens. We have 2 of each on the right. I need a 2 in front here. That's going to change both of these values because now I have 2 water molecules. Okay, and so my oxygens are now balanced, 2 and 2, but my hydrogens are not, so I need a 2 in front of the hydrogen to balance those out. So it's almost like a game of Sudoku. You have to go back and forth changing the coefficient until the number of atoms match up. For sodium and chloride, I didn't leave myself room here. Little tiny T-chart. I have 1 sodium, I have 2 chlorines, and then I have 1 of each on this side. So I need to fix the chlorine by putting a 2 here, but that multiplies both of them by 2. Whoops, equals 2. And now I need a 2 in front of the Na, and that one is balanced. Okay, for this one, this is tricky because this chlorine only comes in multiples of 2, while this chlorine only comes in multiples of 3. So for this one, we need a math term called the least common multiple. The least common multiple of 2 and 3 is going to be 6. So I need 6 chlorines on the left and 6 chlorines on the right. Let me show you what I mean. I have iron, and I have chlorine. Iron and chlorine. 1 and 2, 1 and 3. So there's no way to balance the 2 and the 3 without making them both equal to 6. So I need to multiply this one by 2, 6, and that also multiplies the top one by 2. And then I need, whoops, and I have to put the 2 out in front. There's my coefficient of 2. I should have used different colors. I'm sorry about that. And I'm going to multiply this one by 3. I need a 3 right here. So that gives me 6. And last thing is to balance the irons. I had 2 on the right, so I need 2 on the left. And this is my balanced equation right here. Okay, so I should rewrite that to make it a little neater, but you guys can rewrite it on your own. Last but not least, I have carbon, hydrogen, oxygen, carbon, hydrogen, and oxygen. Okay, a little T-chart, 1, 4, and 2. 1, 2, and 2 plus 1, which is 3. So we need to fix these. The carbons are already balanced. The hydrogens need to be multiplied by 2. So I need a 2 right here. I'm going to make it purple. So 2 right there means this is times 2. And this one becomes 2. And so the total oxygen becomes 4. Okay. And now to fix that on the left, that fixed my hydrogen problem. So now I just have to fix the oxygen problem by putting a 2 right there. Okay, so now check, check, and check, they're all balanced. All right, you are going to do some practice yourself. Do not worry about this worksheet. I have another practice for you to do. If you want to try these practice problems on your own, you can. The answers should be in your book. And I'll see you guys tomorrow. Bye-bye.